So that's just an overview of how to analyse survival data or time to event data in an individual trial. When we come to do a meta-analysis of these individual trials, the effect measure that we're interested in is the hazard ratio. But when we do a meta-analysis, we work on the log scale. So what I'm going to refer to now is going to be the log hazard ratio and its variance. So if we've got K trials that are included in the meta-analysis, and for each of these trials, we have an estimate of log hazard ratio and the variance, then we can do a simple meta-analysis and obtain a pooled value across all of these trials by just using a standard inverse variance weighted average method, which is shown here in these two plots. In practice, of course, we'll use software to do a meta-analysis, and that pooling can be done using that software. So if you're using RevMan, then you can use the generic inverse variance option in RevMan. In Stata, it's the metan command, and in R, it would be the meta command. So as a reviewer undertaking this meta-analysis, you need to obtain an estimate of log hazard ratio and standard error from each of those studies, so rather than the variance. And the standard error is just the square root of the variance. On this slide, you can see the kind of information that you need to input into RevMan, and also what results are displayed in RevMan. So there are 5 studies here, and we're inputting the log hazard ratio and standard error, which are provided there in those white boxes. Then RevMan will calculate the study level hazard ratio and confidence interval, as well as the pooled hazard ratio and confidence interval, which is shown in blue there. And also RevMan will create the corresponding forest plot for that analysis. And that will be very similar in other software packages as well. However, in practice, it's very uncommon for the hazard ratio and variance to be provided directly. And there's other various types of information that might be reported in medical journals. So this is an example of the kinds of information you might come across. So here we have a trial reporting that the median survival was 14.5 months for GEM-CCRT patients compared with 6.7 months for 5FU patients. There's a p-value of 0.027 and reference to a figure which is the Kaplan-Meier curve. Then they present 1 and 2 year survival rates for the 2 groups, and then finally tell us that all deaths were cancer related. So there is some information there, but it doesn't tell us what the hazard ratio is, and we can't calculate, can't easily extract the variance from that information. And this is a common problem for meta-analysis of time to event data when we want to extract this data. There's been a number of reviews of the reporting of time to event data in the medical literature. This early review in 1995 showed that the log rank and multivariate analyses were frequently reported only as p-values. And in a more recent review, only around half of the trials actually report an estimated hazard ratio. So there is this need for time to event data to use other information in order to estimate log hazard ratio and the variance. And a number of methods are possible, and these have been discussed in detail in this paper by Max Parmar and colleagues back in 1998. And what I'm going to do now is just go through each of these methods, illustrate the methods with examples. There are a number of equations. As I said before, you don't need to worry too much about the equations, but just think about the concepts. And then I'll introduce at the end a spreadsheet that's available where all of the information can be input into the spreadsheet, and all of the calculations that I'm going through now will be automatically undertaken in that spreadsheet. So you don't necessarily need to be able to reproduce these calculations because there are options available to do that. So the first method is a direct method where we can incorporate or extract information on the log rank observed and expected number of events from a trial report. If we have that kind of information, These are the equations in box 1 and box 2 that we might use in order to estimate log hazard ratio and the variance for this particular trial. So in the top box, number 1, we would need the observed number of events in the research arm and the observed number of events in the control arm, and also the log rank expected number of events in both arms. Whereas for equation number 2, we would need the observed minus expected in the research arm and this estimate VRI, which is the Mantel-Hansel variance of the log hazard ratio. So let's have a quick look at an example. So here's the randomised trial of neoadjuvant chemotherapy in oropharyngeal carcinoma. The authors have presented results from a log rank test in table 5, and there's 2 outcomes here, survival and disease-free survival. I'm just looking at the top half of that table, which is results for the survival outcome. You can see there that they present the number of deaths observed on chemotherapy and the no chemotherapy group, and also the expected number of deaths in both of those groups. So these are the total expected number of events using that formula that I introduced before for the log rank test. They also present O-E statistics and the variance of O-E, and also the corresponding log rank test p-value of 0.03. So there's a lot of information there we can use. We could actually use either equation 1 or 2. This illustration here just uses equation 2. They give very similar answers, so it's not that important anyway. Log hazard ratio is just the O-E divided by V, which is minus 14 divided by 40.7, giving a value of minus 0.34. The variance of log hazard ratio is 1 over 40.7, which is a value of 0.02. And the corresponding standard error is the square root of this, which gives us a value of 0.16. So we would then, for this particular trial, we'd enter the log hazard ratio and the standard error values into RevMan, and it would calculate the hazard ratio and confidence interval for that trial, which gives us a value of the hazard ratio of 0.71 with a 95% confidence interval ranging from 0.52 to 0.97. And so you can see there that the confidence interval for the hazard ratio excludes the value of 1, indicating that this is statistically significant, and that's supported by that previous p-value of 0.03. And this hazard ratio of 0.71 is for the hazard of death on chemotherapy, indicates that the hazard is about 70% of the hazard without chemotherapy, or in other words, there's a reduction of around 30% in the hazard of death by taking chemotherapy. The second direct method that you could use incorporates or extracts information from a Cox model that might be presented in the trial publication. So the report might present the regression coefficients from the Cox regression model, in which case these are direct estimates of log hazard ratio and the corresponding variance or standard error. Excuse me. So that's very straightforward to use that information. It can be input directly into RevMan. Just be careful though that you're aware of what has been included in the Cox regression model if this is the information you're extracting. It may be that the Cox regression model has just included the risk factor for treatment, in which case the hazard ratio, the log hazard ratio, is an unadjusted effect. However, if that regression model also includes other variables such as age and sex or severity of disease, as is commonly the case in trials, then the hazard ratio is an adjusted effect, and it's not necessarily going to be compatible with other estimates of hazard ratio in other trials that might be based on other methods such as the log rank analysis. So you need to be careful and be aware of what has been included in the Cox model if you're using those results. The third approach, again a direct approach, is where we might be presented with a hazard ratio and a 95% confidence interval. So here we can use the hazard ratio directly, and we just need to do a little bit of manipulation of the confidence interval data in order to provide the variance of the log hazard ratio, and that's given by the formula in box 3. So it's simply the upper confidence interval of the log hazard ratio minus the lower confidence interval of the log hazard ratio divided by 2 times 1.96 if we're referring to 95% intervals, and that value is then squared to give the variance. So here's a quick example. This is a randomised phase 3 study of 5-FU versus methotrexate and 5-FU for advanced gastric cancer. The results are presented there, and you can see at the bottom in red that the MF arm was not superior to the 5-FU arm with a hazard ratio of 0.94 and 95% confidence interval ranging from 0.72 to 1.22. So using equation 3 that we just looked at before, we can estimate, first of all, the log hazard ratio is calculated by taking the log of 0.94, giving a value of minus 0.06. And we then input the values from the confidence interval into equation 3 to give us the variance. So notice there that we're actually using the logarithm of the interval, the confidence interval limits there. Make sure that you're using the log values rather than the direct values. Just a note as well, if you are using RevMan, there is a facility in the generic inverse variance approach where you can click on the little calculator, and that will allow you to be able to calculate log hazard ratio and standard error directly. So you just have to input the hazard ratio and the 95% confidence interval into those boxes, and it will do all that calculation for you. So that's quite handy to remember that. So the fourth method that I'm going to talk about is an indirect method using information that's presented on the log rank test p-value and information about number of events and number of patients in each group if that's given. So here's an example of results from a trial where they refer to the number of patients in the treated group is 21 and 19 in the control group, with a p-value there right at the bottom of 0.00006. So we can use this information, and there's 3 different approaches we can take. The first 2 are relevant if we've got equal numbers randomised in the 2 treatment groups. So the expression in box number 4 is going to be used if all we have is the total number of events across the 2 groups. And the expression in box number 5 is used if we also have the number of events available in each of the treatment groups, research arm and the control arm. In practice, they'll give very similar results anyway. So both of these approaches will estimate O minus E and V for this individual trial, and we can then plug that into the equation that we saw before to obtain the estimate of log hazard ratio and variance. So if the number randomised in the 2 groups is unequal, then there's a slight modification to the equation where we're also incorporating information about the number of patients in the research group and the number of patients in the control group. And as I said before, once we've got the O minus E and the V values, we can then use this expression, which we've seen before, in order to obtain the estimate of log hazard ratio and variance for this individual trial. So if we go back to that example that I just introduced, we're told that we've got 21 in the treated group and 19 in the control group, and all but 1 patient died within 2 years. So we know that from that information there's 39 deaths overall, and we also have this p-value 0.00006. So we'll use equation 6 because there's a slight imbalance there in the numbers randomised, and we've got the total number of events 39 and the p-value there, and we can plug all of that information into those equations presented before. That gives us a value of O minus E of 12.5 and V is 9.7. And from equation 2, the log hazard ratio for this particular trial is O minus E divided by V, which is 12.5, divided by 9.7, which is a value of 1.29. And the variance is 1 over V, which is 1 divided by 9.7, or a value of 0.1. And the standard error for that is 0.32. So if we input the log hazard ratio and standard error into RevMan, we'll then obtain an estimate of hazard ratio of 3.63 with a 95% confidence interval ranging from 1.94 to 6.8. And so the hazard of death in the control group is over 3.5 times the hazard in the treated group. This confidence interval, you can see, excludes the value of 1, so it's statistically significant, and it excludes 1 by quite a big, by quite a long way, and that's supported by this very small p-value that's provided. Now also notice here that the formula here is only going to give you a positive value of log hazard ratio, and so the hazard ratio is going to be greater than 1. So you have to be careful with understanding the direction of this effect and making sure that it's consistent across all of these trials in the meta-analysis. So there was extra information in this trial which indicated that the control group had the worst prognosis. And so because the hazard ratio is greater than 1, this must be in terms of a comparison being made of the hazard of control group compared to treatment group. If we wanted to switch that direction to be consistent with other trials in the meta-analysis, that might be comparing the hazards for the treatment to control group, which is the more traditional approach, then we can just take the negative of the log hazard ratio and that will then switch that order around. So just be very careful you understand which way around the hazard ratios have been calculated to make sure that they're consistent across trials in the meta-analysis. So I've presented there a number of approaches based on information that we can extract from the manuscript around the Cox model and also the log rank test and the p-value. And there is a clear hierarchy of approaches there, and those methods are generally very reliable. However, in some cases we might not have any of that information, and all of the information that we have available might be published survival curves. And it's still possible to use this information, but we should also obviously make sure that those other methods are not possible first. Okay, so before we move on, if you have a quick look at this survival curve here, comparing the survival of the treatment group and the control group, what do you think is the approximate chance of surviving to 60 weeks in the treatment group? Is it 5%, 30% or 70%? Okay, so I can see that 80% of you have gone with 30% as the survival probabilities, and that's the correct answer. So we look across at the time axis at the value of 60 weeks, draw a line up to the survival curve for the treatment group, and then across then to the corresponding survival probability of 0.3, or here on this scale it's 30%. And that's going to be important to understand that, because that's the kind of information we want to extract from the survival curve for this final method based on the Kaplan-Meier curves. So there's two approaches we can use to incorporate information from published survival curves in order to estimate log hazard ratio and variance. The first was proposed or summarised by Parmar et al. In the Statistics in Medicine paper in 1998. And in that approach, we're not using any information from numbers at risk for the curve. So if you don't have information on numbers at risk published in the curve with the curve, then the Parmar approach is the one to use. However, if the trial publication also presents numbers at risk, then we can use this additional information to tell us more accurate information about the censoring pattern. And so we would use the extended version of that method, which has been described by Williamson et al. In a paper in 2002. So the approaches are very similar, and don't be too concerned about the actual the methods. Both of these papers do go into quite a lot of detail about how the algorithm works. However, this has all been translated into an Excel spreadsheet, which I'll refer to at the end of the webinar, and all of the calculations are conducted within that spreadsheet. So essentially, if the only information we have is a published survivor curve, we first of all, we need to take the curve, and for each of those trials where we have a curve, we would split the time axis in that trial into t non-overlapping time intervals, and we would choose these to limit the number of events that occur within any time interval. So we need to look at areas of the curve where the curve doesn't drop down too drastically, because that would indicate that there's a lot of events happening within that interval. So in that case, we might need to look at much finer intervals of time. Then for each of those intervals, for each treatment arm, we would then read off the corresponding survival probability in the same way we just looked at in that example before. And then step 3 onwards, we would use these probabilities together with information on the numbers at risk if they're provided. And if they're not, then we would need to also incorporate information about the extent of follow-up in order to make an assumption about the censoring pattern in that trial. So if I just have a quick look at this example here, this is a survival curve comparing time to progression in 2 groups, gemcitabine and gemcitabine in combination with CDDP. Now I've had to actually label the treatment group here because the survivor curve is very poor in this journal article, and it's very hard to distinguish between the 2 groups, even though there's the key there for the graph. And that's the kind of problem that you'll come across when you're extracting information from these published curves. The quality is not always great, so it does put into question sometimes the reliability of these methods. So for each of the treatment groups, we look at a particular time interval here. So roughly at 6 weeks, we would read off the survival probability of 0.78 in the gemcitabine group. Then at around 13 weeks, this is dropping down to 0.42. And at 22 weeks, this drops down to 0.24. And we would do the same in the combination group. So at 6 weeks, it's around 0.95. 13 weeks, it's about 0.65. And then 22 weeks, it's about 0.39. So we would extract all of that information and input that into the spreadsheet, which I'll show you later. If we're using the Parmar method, then we also need to extract information about the minimum and maximum follow-up time, and that's so that we can make these calculations, and we're making an assumption here of uniform censoring occurring within these intervals of time. So we can see here in this diagram that Fmin is the minimum follow-up time, which is the time between the date that the last patient's randomised up until the date of last follow-up, whereas Fmax is the interval of time between the date the first patient's been randomised and the last patient's been followed up. If that information is provided directly, then we can just extract that information. However, it's very often isn't presented in that format, and so we might need to look at other information in the publication in order to estimate these values. So for example, if we know if the curve presents censoring tick marks on the curve, we can assume that the first tick mark is equal to Fmin and the last tick mark is equal to Fmax. The publication might present the median follow-up and accrual period, so we can calculate Fmin and Fmax using those expressions there. Or we might, for example, be provided with the date of final analysis or date of submission of the manuscript to the journal, and we can make some assumptions about about these dates and use these expressions given in 3 and 4. And there's a lot more detail provided on this and examples of this in the Tierney et al. Paper. There's a reference there for you. So essentially, if you don't have numbers at risk on the curve, you will need to extract Fmin and Fmax. However, if you do have a curve which does present numbers at risk, as in this example, and this is actually quite a nice, good quality survival curve, then we can also extract those numbers at risk at those time points and use that information using the Williamson approach. So we don't need Fmin and Fmax for this approach. So just a quick note about zero events and these survival curves. You will come across difficulties if the estimated number of events within any of those intervals on either arms is 0, and that will happen when within that interval there's no change in the curve, so it's not dropping down at all. And in that case, the advice is to replace the 0 by a very small number of events in that interval. And this is then the best estimate of the total number of events and overall variance in each arm, and is preferable to combining time intervals to get around that problem. So the approaches that I've been through just now that have been described by Parmar et al. And also the extension for the numbers at risk in the Williamson et al. Paper. So those papers are quite technical, but they have been translated into a more easy to read format by Jane Tierney and colleagues in this trials paper. So all of those methods are described in detail in this paper, and there's nice clear examples as well, which help to understand those methods. They also in that paper provide a template data extraction form for you to use if you're considering extracting time to event data for a particular trial. So that's a really useful tool as well. And then finally, they also present a spreadsheet to facilitate the estimation of these hazard ratios from any of these summary statistics that we've been through today, and also from the extracted Kaplan-Meier curves. So there's a link in the paper, it's also provided there. So I do recommend highly that if you are doing a meta-analysis with time to event data, definitely use this approach, because it avoids the need to have to do all these calculations by hand.